end of the talk, if you have any feedback regarding the notes that for I think that they were according to the not that according to the exam based on the second language. So I think and there will be somebody here who may not know what Riemannian manifolds are. Are there people who know what Riemannian manifolds are? Okay. Fine. So are all of you acquainted with smooth manifolds? Or do I need to yes, no? Is that nice? Okay. All right. So what I want to talk about is this basic sort of setup called Morse theory. Starts in a very basic sense, but hopefully by the end of the third talk I will be able to show you some glimpse of where this could lead to, and it could lead to many interesting and technical things. So what you essentially do is you're studying So the aim for all the three talks essentially is to study via analysis and geometry real value functions defined on smooth manifolds. So for the time being, if you are not sure what a smooth manifold is, take it to the Rn. So Rn is the standard n-dimensional vector space. It has a topology and a notion of smooth maps into it and smooth maps from it. So if you take this to be, I'm going to denote it by n. This is usually F for the manifold and this for the dimension of the manifold, but you can take it to the Rn. And we're going to study smooth real value functions or smooth scalar value functions on Rn. From calculus, you know what you do when you have a smooth function. So if you don't have smoothness, just continue to look at its maximum and its critical points. But if you have a function which is at least C1, you should differentiate and look at its derivative and see where it's zero. And that gives a critical point. So one way to start this off is to look at maps from Rn to R. Right? And we want to sort of study this. There could be several critical points, but we'll soon zero in on a notion of critical points being nice. That notion, of course, is tied to the function f itself. And we'll see what a critical point being nice in more standard terminology, which the critical point is nice if it's not degenerate. And that definition requires us to go through the Hessian of this function. So for those who might haven't heard the term Hessian, think of it as the matrix of double derivatives. Right? So you have f is defined on x1 through xn. So if your f is C2, it is twice differentiable. You can look at del 12 by del x and del x. That gives you an Gaussian matrix. Right? And so that matrix captures something about the behavior of the function f at the critical point where you want to analyze it. So we're going to study critical points as well as symmetric linear form. So this is essentially going to take us a bit of time to establish what goes on. So the whole point is you want to study this global function, but you want to see how the level sets change as you pass through critical values. So again, I will essentially borrow the first few pages of Miller's book and give you some pictures, and then hopefully by the end of this talk we'll be able to justify what we do. So there are two references for this. Well, there is the original paper by Moore. Just put it up. and more stem cells. Of course, as is almost customary in mathematics, once piece of mathematics is written up by John Wimber, that becomes a definitive reference. So that's it's a wonderful book, and if you ever want to start out on the topic of course, there are modern texts as well, but this should be the first book that you should Alright. So the point is you want to understand this object M or Rn, whatever the case may be. And when I say understand this, I mean you want to understand the topology and geometry of this object via some chosen real value function and by understanding the critical points and what happens when you go through the critical values. How do the levels change? So let's draw the simplest example first. So let's take a sphere. We have the height function, right? So this is call it h. So when I say this is the height function, what is my understanding? My understanding is that h is a graph defined on S2, which is the unit sphere in R. So this is x, y, z, x squared plus y squared plus z squared is 1. This maps to R, right? What is the map? Well, the map is, as the name suggests, it's the height. Right? So x, y, z goes to the height function. This function has two obvious critical points, right? It's a smooth function because it's a restriction of a linear map from R to R. It has two critical points. One is this. I'm sort of not drawing it on the top, just imagine this to be sort of slightly tilted towards you. So this is here, so the other one should be at the back. So okay. I think most people will be happy with this. So this is the north pole, this is the south pole, and this takes values between -1 and 1, and this is the global map, the global input, and you can convince yourself that this has no other critical points. So yeah, for those who just for completeness, you say that P belongs to Rn. Since we are defining this from scratch, if what happens? Look at the derivative, look at here, or you will think of it as saying del f by del xi at p is 0 for all xi. You have seen tangent spaces, it's equivalent to saying that when you linearize f, it gives you a map from the tangent space at p to Rn. The tangent space at f of p, that linear map is 0. They're all equivalent. So you think of this and also saying del f at p. Although I don't want to use this particularly because this in general becomes a coordinate dependent thing. It's better to think of it as saying this linearized version of f as a linear map at the tangent space. Yeah. So these are the only two critical points. Okay? And let me draw one more picture. And this also has a height function. Yes, that's slightly bad on my part. And these two lines are disjoint. So this is for this and for that. So here, of course, there's a global mass and there's a global mean, right? What other critical points are there? At least for those who haven't seen this before, just from the picture or otherwise. So I'm not giving you the function here because I'll express this function very soon. In another example. So let's just take it for what it is. Imagine this to be one of these swimming tubes. You make it stand on the top, so you will touch the floor at some point, and you have a topmost point, and then you have a couple of other critical points. So which 2 points get those speed? So for those who haven't seen this example, any cases, which point point can be from physics ideas or otherwise.
The genus points. The point. Yeah.
This one?
Yes.
Okay.
And lower one.
Yeah, so by symmetry, that is a critical point, this also has to be, right? It turns out these are the only, so apart